What is a monad?
Monads are a concept that was invented in mathematics.
A few months ago when I was getting into functional programming, despite having watched many monad tutorial videos and read many articles, I still couldn't fully grasp the concept of monads. It almost seemed like the only way to intuitively know how monads work is by actually learning a functional language.
That's the only way that we stand a chance of winning.
So that's exactly what I did. I learned Haskell. Now that I get what monads are, I want to take on the challenge of explaining what a monad is to people without requiring knowledge of functional languages. Without further ado, let's get started. Before we get into monads, let's first revisit the map function in arrays. What map does is apply a given function to each element in a given array. The type signature for map is this. The first parameter is an array, the second is a function, and it returns a new array. In this example, T and U happen to be of the same type, number. If you're not familiar with type signatures, check out my previous video on currying. Now, let's examine a crucial operation related to monads, flatMap. Let's say we have an array containing the numbers 1, 2, 3. If we flatmap this function over it, we get 1, 2, 2, 4, 3, 6. Here's a little animation to illustrate how it works. Applying this function to the elements in the array gives us the arrays 1, 2, 2, 4, and 3, 6. If we concatenate these arrays together, we get 1, 2, 2, 4, 3, 6. That's basically how flatmap works. Simple, right? Now let's look at flatmap's type signature to better understand its functionality. Its first parameter is an array, with the second parameter being a function, and it finally returns an array. Compare the type signature of flatmap with that of map, and you'll see the key difference is in the second parameter, namely the function they take. Flatmap takes a function that transforms an element into an array of elements, while map takes a function that transforms a value into another value of the same or a different type. Notice that flatmap is a more powerful operation than map. This is because everything that map can do, flatmap can do as well. For example, this usage of map can be replaced with flatmap like this. However, not everything that flatmap can do can be done by map. Now that we understand how flatmap works, let's consider a hypothetical JavaScript-like language. In this language, in order to better differentiate between pure and impure functions, we'd like to have the restriction that all side effects must be defined in types. For example, if a function performs any IO operation, it must return an IO type. For instance, consider the type of console log. Its input would be an array of any type, with the return type being IO void, because it performs an IO operation but returns no value. As another example, consider reading a string from user input. The type of the function readLine would be something like this. It takes a string as input and returns an IO string, because it performs an IO operation and returns a string. Now let's try doing something different. Suppose we want the user to input a number and we want to multiply it by 2. We define the return type of the function to be IO number because it's going to perform some IO and return a number. Since the return type of getInput is also IO number, we can't directly multiply it by 2. How should we do it then? Take a moment to pause and ponder if you need to. Here's how we do it. Assuming the type IO is a functor, meaning it implements the map function, then we can map a function over it to multiply the value wrapped inside it by 2. Find it familiar? This is very similar to using .then with promises. Now, what if we want to add 2 input numbers? Maybe we can try using map? Well, now we've got nested IO, which is not the return type that we want, so that doesn't work. Remember flatMap, which we introduced earlier? The type of flatMap for arrays looks something like this. It takes an array and a function and returns a new array. If IO also has a flatMap, the type will look like this. Since flatMap removes the additional layer of I/O, with the help of flatMap, now we can add two numbers and obtain the sum. In other words, flatMap allows us to chain two operations with side effects, something we couldn't achieve without using flatMap. If you compare it with promises, you'll notice that they're very similar. So, what actually is a monad? As we discussed in the last episode, a functor is a type that supports the map operation and also satisfies certain mathematical properties. Similarly, a monad is just a type that implements flatMap, which is an operation of this type. In addition to flatMap, a monad also needs to implement another operation called unit, which encapsulates a value within the monad's context. For example, in the context of an array, square brackets serve as the unit function. In the case of a maybe, this is the equivalent of unit. Both operations go by different names in different languages. For example, flatMap is also called this thing or bind. Unit is also called return. Just remember these are just different names for the same operations. As mentioned earlier, a type has to satisfy certain mathematical properties to qualify as a monad. As I don't think these properties are important to build a good intuition for understanding monads, I won't go into details in this video. Feel free to explore this topic further by reading this article if you're interested. You've likely noticed a close relationship between JavaScript promises and monads from our previous examples. But how are they exactly related? Well, as we've seen in a previous example, .then serves the role of both map and flatMap. Array qualifies as a monad because it supports flatMap. So does this mean a promise is also a monad because .then can do the same thing flatMap does?
JavaScript has something very close to monads. I don't remember the details. Apparently, promises in JavaScript are not quite monads. I don't remember what they screwed up to make it not a monad.
While promises come close to being a monad, they don't satisfy some monadic properties. So technically, they're not a monad. But for the purpose of this video, we can essentially treat it as a monad since it's close enough. Let's try to answer another interesting question. What is the relation between monads and functors? Previously, we learned that flatMap is a more powerful operation than map in that we can do everything map can do with flatMap. So basically, every monad is also a functor because it supports a map operation. But not every functor is a monad. Now I want to introduce a commonly used construct in functional programming, do notation. As you may already know, async await is just syntactic sugar for .then. Essentially, they accomplish the same thing. The async await syntax just makes the code more intuitive in certain cases. This raises an interesting question. If .then can be expressed using async await, can we invent an async await-like syntax for all monads? The answer is yes. In functional languages, we have this thing called do notation, which is very similar to async await. The only difference is that do notation is applicable to all monads, not just promises. Let's make it more concrete by imagining a JavaScript version of do notation. In this imagined syntax, we will replace async with do and await with bind. Let's look at a couple of examples to better understand this new syntax. The last example is pretty mind-blowing if you haven't seen it before, so be sure to stay till the end. In this example, we use await to fetch user data. Using our new syntax, the code will look something like this. The transition is pretty straightforward with promises, but what about other monads? In this example, array is the monad we're working with, and this function returns an array of arrays. What value do you think this function will return? Before delving into the explanation, let's familiarize ourselves with the concept that arrays represent the effect of choices or possibilities. Consider this function. It takes a number as input, representing an initial position, and returns two possible next positions. What if we want to know all the possible positions after two steps? You may have noticed we can chain this effect using flatMap. Let's try to chain this operation by using flatMap. With the initial position set to 0, this will return the possible positions after taking one step, which are 2 and -1. And this will return the possible positions after 2 steps, 4, 1, and -2. Since do notation is just syntactic sugar for flatMap, this function on the left does the exact same thing as the function on the right. Having looked at a simpler example, let's return to our initial example. Here's what the function will actually return. Can you figure out why? With arrays out of the way, let's look at another very common monad, maybe. Consider this example. Suppose operation A could either return a number or fail. Operation B could also either return a number or fail. In the maybe type, we represent success with just and failure with nothing. So both A and B return a maybe. Now, let's consider how to sum up the results of operation A and B. This is what we ultimately want to achieve with do notation. But in order to use do notation, maybe has to be a monad. In the last episode, we only defined map for maybe. So now we have to define a flat map for it as well. Here's the definition. We first check if the maybe has a value or not. If not, we return nothing. Otherwise, we apply the function to the value inside the maybe. With flatMap defined, we can now use do notation to sum up the results of both operations. This is equivalent to using flatMap directly to sum up the results. Let's dive into the mind-blowing example I mentioned earlier. We'll start simple. We have two functions. Add2, which adds 2 to the input number, and mult3, which multiplies the input number by 3. Here's an example of using these functions. We set the initial value to 1 and call add2 and then mult3, giving us a result of 9. Essentially, we're performing this simple calculation shown on the screen. Here comes the interesting part. What if we want to keep a log of all the operations done? Instead of 9, we want this object to be the end result. To accomplish this, we can modify add2 and mult3 to include log concatenation. This allows us to execute the same operations while keeping a log. However, this leads to a lot of duplicated code. With this approach, whenever we add a new operation, we need to write the same concatenation logic again. Ideally, we want to abstract this away. As you might have guessed, we can model this effect of concatenation of logs with a monad. First, we'll define a type called withLogs to represent our monad. Second, we'll create a function named unit, which simply encapsulates a value within the monad, initializing it with empty logs. Next, we'll define flatMap, which applies the input function to the value wrapped within the monad, and appends the new logs to the existing ones. Finally, we'll define add2 and mult3, each of which will return an instance of withLogs. Note that we don't need any log concatenation logic this time. With flatMap and unit defined, we've got a valid monad. Now we can employ do notation to carry out the operations as before, but this time with logging. We can also achieve the same result without using do notation. Here's an interesting twist. We're going to introduce this function called tell, which creates a withLogs instance with an arbitrary log entry but no value. This function will allow us to insert any random log message at any point, almost as though we have a global state, yet the entire function remains pure. If you're somewhat puzzled by how this seemingly works like magic, try converting it back to using flatMap, and you'll see how it all works under the hood. This is valid TypeScript code, so you can try run it on your own computer. Okay, that's a lot of examples. I only managed to fit 3 examples in this video, but there are many other monads out in the world. You can even define your own monads as long as they satisfy the monad rules. Let's do a recap of what we've learned throughout this video. Initially, we wanted to define all side effects in the type system, but we realized that we couldn't chain effects together. That is, unless we use flatMap. flatMap allows us to chain effectful operations together, and the types that implement flatMap are called monads. So that's basically it. To sum up the entire video with one sentence, monads allow us to chain operations together under the restriction that all effects must be expressed in the types. This video focuses more on building an intuition for what a monad is. If you want to explore this topic further, I highly recommend reading the original monad paper by Philip Wardler, which I will link in the description below. Hit the like button if you like this video. Let me know what you think in the comments section, and I'll see you guys in the next one.